Okay. So, last time, we started looking at Gauss's law, right, which was a really useful thing. We defined what electric flux was, and we talked about some useful ways to find electric flux. And today we're going to be discussing how we can use Gauss's law to actually make a lot of very, very, very complicated integrals to mostly simple geometry problems more than anything. Right? So this is kind of a review from last time. The first thing that we see here, so Gauss's law is particularly useful when we're talking about a closed surface. So we had that definition for flux that said, okay, E dot dA, take the integral of that thing, right? The electric field passing through some sort of area, and that was how we define electric flux. But for Gauss's law specifically, we say, what if we enclose some charge? So now there's a definitive inside and a definitive outside. There's no holes or anything else, right? If I poked a hole, if here's my Gaussian shape, if I poke a hole in it or something else so that we can see on the inside, no longer a closed shape. Has to be completely closed all the way around. But as long as we're completely closed, then the flux through this surface is defined as Q inside divided by E naught, and that's it. No integral, no electric field, no area, just the charge inside. And this is what I call the first Maxwell equation, the first of what we will eventually find to be 4 Maxwell equations. But this is a pretty important one to start, and it's our first instance of looking inside as to defining all of electromagnetism, which is kind of a big order. But so that was kind of cool on its own. But let's do some concept checks real quick, mostly from last time actually, to see how much we remember from last time conceptually. Surfaces A and B have the exact same shape and the exact same area, and they're lined up next to a point charge as shown in the picture. Which of my two surfaces is going to have the larger electric flux? What do we think, team? And I want to make sure you know that these are not closed surfaces. There's no charge inside. We are just looking at two plain old sheets. Gauss's law does not apply here. Here's what we've got to figure out. For both of these shapes, they have the same area A, right? The same area A, the same orientation of A, right? They're both kind of standing vertically like this. So the area is not going to make a difference. The orientation of the plates is not going to make a difference, roughly speaking. The much more important part, then, is which one is going to experience the stronger electric field. And that's actually a little bit of a complicated question, because if I look at these things, we can see through either one of them, the electric field is not constant through that surface, right? It's constantly changing strength and changing direction, so it's not a simple question. However, as I'm looking at this thing, if I'm trying to compare the two, A has many more field lines passing through it, and the spacing between those field lines is much smaller as compared to B. Surface A has our larger electric flux. All right, so let's look at concept check number 2. I have some sort of shape here. I have a side A, which, let me highlight this one. This is A. It's a back-facing plate. Face B is this big square on top. Which surface has the larger electric flux magnitude? A or B? Let's think about this one for a little bit. So, they are going to be equal, but let's talk about why. I've got a few different metaphors that I can use to try and describe this one. So, part of this is going to be the fact that if we're looking at this thing, so there's a few different ways that I can think about this. I don't know anything about whether or not there's charge inside. Like, technically, if I'm looking at this thing and there's a uniform field, I can say for the entire shape, the net flux should be 0. Right? That's one thing that I can say immediately. If there's no charge inside of this thing, and I don't necessarily know that, but they're telling me the electric field is uniform, and if the electric field is uniform, it's certainly not because of any charges inside of here. So the flux should be 0 if I look at every single surface. And then some of these surfaces, 3 of them to be specific, are going to have 0 flux, so the other 2 faces better cancel out. That's one way to think about this. Another way, you could actually go through and do this thing properly. It's conveniently set in such a way that this little line B here actually kind of looks like it's coming off, normal from the surface. The electric field goes like this. So here's E, here's what I'll say A of B. If you find this angle theta right here, you can actually do this dot product. We don't need to know anything about surface A. We could just take what we know about surface B, take that angle theta, and solve this thing out. You've got to figure out what that angle theta is, but there's a trick to that as well, that this angle here, called phi, is the same as this angle here, called phi. There's some geometry that goes into this, but it's a doable problem. But what we're basically seeing here is that despite the fact that they are different areas, the fact that face B is at an angle and is not perpendicular to my electric field means that the electric flux, the electric field is not just straight passing through this thing, right? It's not maximizing that electric flux. There's an angle to it that means we're getting essentially diminishing returns. One way to imagine that is imagine that I'm trying to pass a flow through a certain amount of pipe. If my pipe looks like this, and where's my drawing tools? It always comes up with my drawing tools, but for some reason it's not doing that. Let's take a pipe like this versus a pipe that looks like this. Where are my drawing tools? Here? There we are. I get a flow like this. This one's slanted, right? It's using a lot more material on the sides, but the flow, this height between the two, is the same. That one's a little bit more out there in terms of a metaphor, right? But it's the same kind of idea. Just because I slant this thing, it doesn't mean that I'm now using all of that material in the same way, right? If I had stacked this thing back up, I would have a wider pipe. But if I slanted like this, I match my original height. These things match their height. The flow through each face is going to be the same. One more way that you could think about this, and maybe a little bit of an easier description, is trying to say the same thing, but imagine you don't have stereoscopic vision. Imagine you're just looking at this thing on a computer screen or something. So you can't, there's no sense of 3 dimensions. If I look at this thing from side A, I see a rectangle. Turn it by 90 degrees, I see a triangle. Turn it by another 90 degrees. I'm looking at side B, but I see a rectangle again. If I don't have any depth perception, I just see another rectangle. The effective area that's actually passing through is the exact same area as A. If I define my directions here, call this Y, call this X, call this Z, then what I'm going to end up seeing is that my surface area effectively has some components in the YZ plane and some components in the XZ plane. And only the components in the YZ plane actually matter. Now, when we're actually talking about the vector that I'm talking about is split between Y and X. The X component is what matters from our vector. But remember that normal vector is pointing directly out, orthogonal to my plate, so it looks a little bit different. It's a little bit strange. But those are a few different metaphors to try and describe what's going on here. Hopefully one of those sticks with you, right? Hopefully one of those makes sense. If not all of them make sense, that's okay, as long as one of those makes sense. All right, concept check number 3. Now, I do have 2 closed surfaces. Surface A, surface B. Which one has the larger electric flux? So that's okay though. Let's talk about these things. If I have a closed surface, Here's my normal equation for the electric flux. Right? Fantastic, but kind of difficult here. If I have a closed surface, if I put a little circle around my integral, this becomes Gauss's law. As long as it is contained inside, as long as there's an inside and an outside, a closed surface, then the only thing that matters for my electric flux is the charge inside. Surface A has 1Q. Surface B has 2Q. Surface B has the larger electric flux. And it's exactly double. It doesn't matter what the size of surface B is. It only matters what charge is on the inside. But only when it's a closed surface. There's like a little decision tree for finding a lot of these things. Is it a closed surface? Is it not a closed surface? If it's a closed surface, Gauss's law comes into play. Right? If it's not a closed surface, the integral has to be the way we go. But usually, we're going to try and make that a little bit easier than actually doing the integral. All right. It's just because B has the larger charge. That's exactly it. As long as it's a closed surface, that's the only thing that matters. It wouldn't matter if I put, here's a positive Q that's, I don't know, 50 billion, billion is 12, Q. Would not matter. Does not matter because it's not inside. Doesn't make a difference. It's the really fun thing about Gauss's law. If it was a cube, doesn't matter. Q inside. There's no dependence on the surface area, which is a really fun result. Now, that doesn't mean anything about this middle step about what the electric field is going to look like, right? The electric field outside of a cube might be, who knows, right? That's going to be a little bit more complicated if we had something like that. But as long as it is a closed surface, there is there is some separation between an inside and an outside. There's only dependence on the charge. Yeah, it's a nice fun result. It's very, very useful. So, here's how we're actually going to use this, right? I just threw this word at you, a Gaussian surface, but I really haven't defined that yet. So let's talk about that. We keep talking about flux through a certain shape. I keep throwing things at you, and I don't really specify. We say any shape could be fine. A cube, a dodecahedron, I don't know, a weird, not a Mobius strip or anything, right? That doesn't quite work. But, we can do all sorts of these things. As long as I can define an inside and an outside, it works, and I can find the flux that way. But to be honest, finding flux is really not all we want to do with this thing, because flux on its own is not a very useful term. It does have some places where it is useful, right? Keep that in mind. It does have some places where it is useful. Not things that we're going to cover in super great detail right now, though. Flux is often used more as a stepping stone than anything else. Instead, we want to try and see if we can choose a Gaussian surface, choose one of these spheres that we draw around our charge, so that it's a lot easier to find the electric field of that charge. And the way that we have to do that is we have to be very careful with how we pick the symmetry. We have to be on the lookout for symmetrical shapes and draw a Gaussian surface that matches the symmetry of our object. Right? We're trying to look for the times where we can simplify this integral, E.dA, into just EA. Right? No vectors or nothing else. We want to make this as simple as possible so that we can more or less completely avoid the integral. So, if we have an object that looks like this, we have something that's kind of lumpy, we're going to have a really tough time actually using Gauss's law properly, right? Because that object that we have, that Q in blue, really doesn't have any good symmetry to it. we can draw a Gaussian surface around it. And we can find the flux through that surface by just taking the charge inside. But to extrapolate out the electric field from that is going to be a very, very difficult challenge for us. And you're at a certain point better off just doing the integral, right? It's really not going to give you anything else very useful. So we're going to try and look for shapes that match a symmetry based on one of those three symmetries that we saw last time. So let's go back to this problem that we faced at the very beginning. What about the sphere? We said this is awful. This is a 5-page kind of integral. This is not a fun thing to do, and you've got to do all sorts of three-dimensional integrals and stuff like that, and it gets nasty very, very quick. Can we use Gauss's law to make this problem easier? Well, there's a couple details that I want to emphasize here. If we're looking at a sphere, I'm going to kind of immediately assume that the electric field is uniform depending on only the radius. If we can agree on that, if I can say, let me imagine a point charge at the very, very middle. Let me expand that point charge out, right? Let's think about what the point charge field looks like first. If I put a point charge right here, my electric field goes out, radially outwards, right? And it's uniform all the way around given a certain radius. What if I made that point charge a little bit bigger? What if I made my point charge this big? Can we all agree that, well, it probably looks the same? I make my point charge bigger. My electric field still goes radially outward. It's still the same magnitude of electric field for a given r away from my, now, ball, I guess, rather than a point. Does that make sense? Right? The electric field more or less matches the symmetry of my object. That's an important point. Right? Because if I was looking at this, I could say that at the surface, my electric field looks kind of like this at all points, and this is why it's not a very symmetrical kind of deal. But my electric field would point directly away from my surface at all points. Something like that. Right? It's just that's not a very symmetrical shape. But the sphere, that's a little bit more symmetrical. But let's take these two ideas. That the electric field is radially away from my sphere, and the magnitude of the electric field is going to be the same no matter where I'm at around the circle, as long as I have the same radius. Those 2 points. Okay, so let's look outside the sphere first. I'm going to draw a Gaussian surface that matches the symmetry of my object. If I have a sphere, I'm going to draw a Gaussian sphere, right? That makes sense. That matches the symmetry. I'm going to look outside of the sphere first. So the Gaussian sphere, what I have in blue here, is going to have a radius of little r, whereas the object that I'm trying to study has a variable big R. And this is what I'll often try to do for a lot of these things. If it's a movable value, I'll use little r. If it is a fixed value, that is, if it's based on the object, it'll have a capital R. Okay, so we're set up to use Gauss's law. We have some symmetry, right? That's a good spot to be at. And then we said, okay, well, the magnitude is going to be the same everywhere. And because it's always radially outwards, it always matches that dA of my surface, right? It's always perpendicularly going out of my sphere. So the dot product goes away. It's just EdA now. And on top of that, since the electric field is constant for a given radius, E comes outside of the integral. Nice, right? That's easy. Once we're there, we can basically say, okay, well, now we're just doing the integral over dA. The integral over dA is just the surface area of my Gaussian sphere. That's 4 pi r squared. That's just a sphere. Solve that out, and what do we find? This incredible result right here. The electric field coming off of a sphere is the exact same as the electric field from a point charge. No difference at all. It's the exact same. And so all of these times that I keep bringing up point charges and we assume these two plastic balls with a certain charge on them and they behave like point charges, and we just say, just assume. Here's the proof. We don't have to assume the electric field and the forces, because of those electric fields then, are exactly the same had they been point charges instead. We just count it. We don't care about the outside radius of our sphere. The only thing that matters is the distance away from the center. And that's a really pretty incredible result. That's really useful because that says everything that we've been doing with Coulomb's law is still valid for real objects that have 3 dimensions to them, that have a real volume to them. It still works. Now, that's a pretty easy result. What about if we were looking at the electric field inside of the sphere? Now, our Gaussian sphere is in blue here. It's smaller than my full object. So I can take a lot of the same steps as before, right? I'm going through and I'm just saying, okay, well, it's still, radially outward for the electric field. It's still the same magnitude around the same area. But my Q inside is no longer so simple. What I've got to do is I've got to say for my Q inside, this is the charge density of my object times how much volume I have inside in blue. Volume enclosed by the Gaussian surface, call this V sub G, Gaussian volume. That is 4/3 pi r cubed. How do we find rho? Well, that's based on the object. So that's going to be the total charge divided by the volume of the object, 4/3 pi capital R cubed, right? A slight difference between those two, but that's what I'm talking about. The capital R goes for the object, little r goes for our Gaussian surface. If we combine these two things together, then we find that our Q inside is Q times little r cubed over big R cubed. Oh, the very last thing, let me move myself down over just a little bit for now. What we find is that the charge inside is just the ratio of the two volumes, the volume that I have inside of my Gaussian surface versus the total volume of the object. The 4/3 pi just canceled out. So then we combine everything together and we get this, which is not a point charge anymore, not in the same way at least. And that's a little bit strange, because if we're actually looking at this thing, capital R is a constant. Little r, that's our changing variable. I can redraw my Gaussian surface smaller or larger, right? And that means that my electric field, when I actually look at this, as long as I'm inside the sphere, it's actually linear in shape. But the reason for that being is that when we're looking inside of the shape, think about how these two values are going to change. It depends on the charge inside and the distance away. The charge inside scales with r cubed, but the distance away, that's a 1/r squared. So the electric field, as it's trying to balance those two factors out, is left with just not 1/r, it's just left with r, and we get a linear function as long as we are inside the sphere. We hit the edge of the sphere. We reach that boundary condition. Those two values better agree. And if we plug in r is equal to capital R, we do find that they agree. Then from then on out, it behaves just like a classical point charge. So this is how you essentially talk about real three-dimensional objects. As long as you're outside of the object, the electric field looks just like it would for a point charge. So here's our first chance to try it. I have something a little bit more complicated than a sphere, but it still shares that same symmetry. Let's say we have a spherical shell with an inner radius r of I and an outer radius r of O. The shell has a total charge Q, and it's a uniform charge distribution, right? So rho is constant all the way throughout. That makes that a little bit easier. There's nothing on the inside, nothing at all. Find the electric field outside of the shell. Find the electric field on the interior, and then find the electric field within the shell. And that's going to be the trickiest part. Use Gauss's law. Match up the symmetry. So make your Gaussian surface perfectly match the symmetry of your object. And go through all of the same steps that we just saw in those other slides. And let's go ahead and find these answers. Okay, let's go ahead and start talking about this one. And I'm going to really talk through my whole methodology here, how I treat all of these problems, whether it's a sphere, whether it's any sort of object we might encounter. So we have a sphere though, right? A spherical shell, but we can see that it has a radial symmetry. So my Gaussian surface that I'm going to draw here in blue, and let's do a little light blue, needs to match that symmetry. So let's draw it like this. And it almost matches the symmetry, right? It gets pretty close. But here is my Gaussian surface. This is the one that I have picked to be larger than my object. So I've decided that this thing, I'm going to start with a radius little r larger than r outside. So we've got the entire shape inside now. Okay, so I'm going to go through all of the steps that I need to solve this thing. I'm going to start from Gauss's law. The electric flux is equal to the closed surface integral, right over the entire surface, E dot dA. This should be equal, because I have a closed surface, to the Q inside over E naught. And this is my setup for every single one of these, right? Regardless of what I'm doing, this is my same setup for each one. So now we've got some steps that we want to observe. The first being that, okay, well, the electric field is going to be coming off of my object, right? I imagine that my electric field looks something like this, and something like this, and something like this. And the electric field is always going to be radially outwards, passing perpendicularly through my Gaussian surface. That means that the dot product goes away. Whoops, not vector. I don't need the vectors anymore. So that right there is E points radially away. Always parallel. I'll just do the parallel symbol. Always that E is parallel to dA. So our dot product goes away. Okay, now I can also say that, I drew that a little bit too early. I can pull E outside of my integral because E is constant magnitude over dA for a given r. And this is, again, because I picked a Gaussian surface that perfectly matches the symmetry of my object. If I had drawn my Gaussian surface so that it was out here and got halfway in between, I no longer match the symmetry, right? Everything falls apart. I can't use these same arguments anymore. But as long as my Gaussian sphere is centered on the exact same dot that my spherical shell, the object, is as well, we share symmetry all the way throughout, and I can use all of these ideas. So here's these two steps. And now I'm just saying, okay, well, what's the surface area? What is that surface that I'm integrating over? It's the surface area of a sphere. 4 pi r squared. And this dA, this entire time I've been talking about dA as my Gaussian object, right? Gaussian surface A. That's this one. Okay. Now, I've been kind of neglecting the right side of this equation. And all of these things I should specify, these are clever use of symmetry. That's our word for the day. So now we need to look at Q inside. How much charge do we actually have inside? Well, if I look at this thing, all of it, right? As long as I'm outside of the shell, I have the entire Q on the inside. All Q is inside the Gaussian surface. That means that Q inside is just Q. Like that. Now with all that, solve out for E. Rearrange this thing. And what we get is E is equal to 1 over 4 pi E naught Q over R squared. 1 over 4 pi E naught is just K. We get our point charge back out, which is a really kind of incredible thing when you think about it, because what we're saying here is that it doesn't even matter if we hollowed out the inside of one of our spheres of charge or something like that. That's fine. if you take a wiffle ball and you charge up the outside of that wiffle balls are hollow on the inside, it still acts like a point charge. As long as we have a spherical symmetry to our charge, it doesn't matter what that actual object is. It doesn't matter if it's 3 shells intertwined with each other, something like that. As long as they share that spherical symmetry, it's going to behave like a point charge as long as we're outside of it. And that's a pretty incredible result. Now, let's move on to the second part. What happens when we're looking inside instead? So let's do something like this, trying to match that. So here's my Gaussian surface now. My radius, little r. I'm going to go through all the same steps again. I'm going to start from Gauss's law. And maybe you can already see where this is going. How much charge do I have inside? None. Done. That's it. That's all there is. There's no charge inside. There's no electric field. And why is that, though? Because I couldn't make the same argument. I couldn't draw a point charge. I couldn't have a point charge. I asked for that to be in red, thank you. I couldn't have some point charge Q and just randomly draw a Gaussian surface out here and say the electric field inside of that's 0. That doesn't work. Because I am not matching the symmetry anymore. This sphere does not line up with the symmetry of the object that I'm looking at. If my Gaussian surface doesn't match the symmetry of the object, you can't go through this method. It's true that the flux doesn't depend on any of these things. It's true that the flux of this Gaussian surface would still be 0. Flux is equal to 0 because there's no charge inside. But the electric field, we know, is not 0. And we can't use these same tricks that we've been using to avoid the integral so far because we don't match the symmetry of our object. If we had instead drawn our Gaussian surface over the point charge, so that the Gaussian surface is centered on the point charge, then it works again. Then it's totally fine. Right? That's the big difference. Highlight this in red. Caution. Right, and I'll go ahead and draw out the electric field for this thing. So keep that in mind, right? The Gaussian surface has to match the symmetry of the object. But in a case like this, because it does match the symmetry of the object, we're set. The electric field on the inside is 0. And part of the reason for that is being, if I looked at any one of these points, if I looked at this point right here, yes, I am going to get a stronger field from the parts that are closest. However, the parts that are farther away are larger in quantity, and they're going to be pushing back the other direction. The field is still going to cancel out at the end of the day. The field on the inside of this shape is 0. So, on to our trickiest one. This is the one, and I'm going to do this one in green, because I did it last time, but also because, do I want it like that? I want this a little bit bigger than that. So let's do here. Yeah, that looks good. Here's my Gaussian surface now. Now here's a tricky bit. Let's first go through and define the same things as last time, right? So it's still got R, all that good stuff. Okay. Gauss's law, what does it tell us? Got this same piece right here. And I can go through all of the exact same steps that I just did to resolve the left side of this. The integral side of this goes through all of the exact same arguments I saw in part 1. I end up with e 4 pi r squared is equal to q inside over e naught. Here is where it starts to get a little bit different. Because what's my q inside now? It's definitely not the whole q. I still have all of this stuff on the outside. So I can't just plug in q inside is equal to q now, right? And in fact, I'm going to write that out specifically. Not true in this case. What we have to do is look at the charge density. And we need to figure out how much of this charge we actually have. So the first thing we need to do is find that charge density. We'll call it rho. Charge density rho is equal to the total charge divided by the volume that charge is in. And I want to specify that, even if it makes my fraction look a little bit weird and sloppy. Right? I really want to specify that because we can see in the inside here, there is no charge. This big gap in the middle will not contribute anything. So we need to find the volume that where a charge actually is. That means rho is equal to q divided by the outside of the sphere minus that part inside that's hollow. Can simplify this a little bit more at least. To say rho is equal to, let me pull out the 4/3 pi r outside cubed minus r inside cubed. So here's our charge density. Now we just need to multiply that by the Gaussian volume, right? Almost, but not quite. We run into a little bit of an issue again, because now we're not just looking at the entire volume, right? This doesn't count. It's hollow still. It doesn't matter that I've got my Gaussian surface that includes that. It's still hollow. It still doesn't have any charge. How much charge do I have inside is the part that matters. So I'm much more interested in this bit right here. That bit is the one that I'm after. And I'm going to call that V of G, the Gaussian volume that actually has charge in it. So V of G, I'm going to have a similar looking equation. That's going to be outside sphere, little r cubed, minus the hollow part. Something like this, right? Now, my q inside is just going to be, give myself a little bit more space. We'll leave this side alone for now. Q inside is going to be my charge density times the volume of the Gaussian surface that actually has charge divided by E naught. Plug these things in together. So this is V of G times rho. The 4/3 pi are going to cancel out. That makes that side a little bit easier to handle. And I'm going to do all these things at once here. Let's divide over by this. So we've got that times, now this is my rho times Vg. Which, if we look at this thing, is really still just a ratio of the two volumes. It's more complicated by the fact that it's hollow, but it's still a ratio of the volumes of how much charge do I actually have inside. Oh, and finally, Q. Should not forget that piece. Unfortunately, this doesn't simplify much more than that, right? That's kind of all that this turns into be. But that's okay. Because what we really did was we avoided doing a really crazy integral, right? We turn this into really just a geometry problem. We have to figure out what these volumes are, but that's geometry, and we can do that. Let me write this a little bit cleaner. I can simplify it so it looks nice and pretty like this. And there's our electric field within the shell. So, do we have any questions? It's a little bit long, but it's a lot better than doing a 5-page integral. We just have to be very careful about what all the variables mean and understanding what each step is along the way. And the entire reason that we draw our Gaussian surface is not because it's set at any one particular value, right? Because we can scale this r. By calling it a variable little r, we can scale it to any value we want. We can plug in, if we wanted to find what is the electric field 2 centimeters away from the center, we can plug in that little r and we can find the electric field based on that. Right? This is not just one set magnitude, it is a magnitude within this region. And that's very useful, right? It's no longer just plugging in for one value. So one more thing that we might want to do is check these boundaries. So if we're checking the boundaries, we might look at the outside, right? That is when little r is equal to the outside surface of my sphere. If I plug in what I see over here, this becomes, right? Whoops, r naught squared. We just plug that in exactly as we see it. What about what we had seen from over here? What happens when we plug in over here? Well, this whole thing just becomes 1. So we're left with kq over rho squared. Our boundary conditions agree. What about the inside boundary? Basically, we are expecting E to equal 0. Does it work? When we go over here, we plug that in. We say, okay, imagine if we had plugged in where r is equal to r inside, what do I get? And I know I'm going up and more and more and more at a slant. But what we see is that this term right here goes to 0. Boundary condition satisfied. Right? All 3 of our electric fields agree at the points where they meet up, and that's a good sign for us. That suggests to us that everything was probably done correctly, because it's an unlikely coincidence that everything matches up and we did something wrong. So it's just a nice little way to check your work to make sure that everything kind of makes sense. So, there were a lot of pieces here, and I know there were. This is a long problem. But what I always recommend for a lot of these problems is to talk yourself through every single one of these. Every single thing that I was just saying, talking myself through solving the problem. I'm solving the problem in real time, right? That's what I'm doing. This is my problem-solving method. I look at every single piece and I explain why I'm taking each step. I'm going through each of these things and I'm trying to understand, what does each variable mean? What can I do with each variable? What are the limits of these things? What am I expecting to see and what do I see? But I talk through every single one of my steps to try and make sure that I understand what's going on. We're losing those problems where you can just throw some equations at it and wait for something to stick. You have to understand what the variables mean. And that means you got to be able to describe what's going on. So I'm always going to recommend trying to describe these problems to somebody else, but at the very least, try and describe them to yourself. So let's keep moving on, right? We just talked about all of these different things we can do with a spherical symmetry, but we talked about 3 different symmetries, right? Another one that we can look at is cylindrical geometry, right? A cylindrical symmetry. Our Gaussian surface is going to look a little bit different here, right? To match the symmetry of our object, now we have to draw a cylinder instead of a sphere, right? But this cylinder that I draw, again, these are arbitrary values. I pick an L, I pick an R. I say, let's draw a cylinder with a radius R and a length L. What do we have now? Well, as long as I'm an infinite wire, my electric field is pointing directly away from the wire the entire time, and I'm going to try and go with something like this. So a concept check real quick. If I have a cylindrical shape, if I'm looking for the electric field, or in particular here, let's focus on the electric flux of not the outside of the cylinder, but the 2 caps, right? The 2 end caps that we see right here, the big circles. What is the flux through both of those? Sum them up together. So let's talk about this one. All right. Well, despite the fact that it kind of looks like an area of one of the ends, this too actually kind of invalidates some different things for us. But we'll talk about those pieces. So when I'm looking at D, this one doesn't require an integral. I'll tell you that. So E's out. If I'm looking at D, that wouldn't necessarily be wrong except for the fact that it's looking at something for the length, and these end caps have nothing to do with the length. That's something we'll talk about in just a little bit, though. Needing L for finding the electric field will be something we need, but for the end caps, there's no dependence on L, right? I can make this as short or as long as I want, but it really doesn't matter for the end caps. But I can imagine, what does this field look like? As long as it's an infinite wire, the electric field is always pointing radially away, right? Directly away from the wire. There's no twists or turns or anything else like that. I never see anything like this, right? It's always directly up and away. And if I've drawn my cylinder properly, think about what that means about how much electric field is actually passing through those 2 end caps. Nothing. There's no field passing through the end caps. It is true that the area is pi r squared, but because there's no electric field that actually passes through that, there's no flux. Right? If we can imagine this thing, if I take any sort of a lid or something like this, so let's take this kind of poor lid. Here's my cap. My electric field looks like this. It doesn't actually pass through. Now, if I had a finite wire, stuff would change a little bit. But we're not going to talk about those too much because the geometry starts to get a little bit strange. So the answer for this one should be 0. But the geometry starts to get a little bit strange if we actually have a finite wire. But that's okay, because we've been talking about things in reality like this, and we've been trying to deal with them so far anyways. I have, tangled up among a bunch of others, a very, very, very tiny wire, but it's kind of long, right? Depends on how you're looking at this thing. Maybe it's a long wire, maybe it's a short wire, something like this. If I wanted to know what the electric field is at the tip of my finger right here, I can argue that this wire is much, much longer than that distance away. I might as well assume it's infinite. But if I was trying to find the electric field all the way here, now there's a much greater difference. That much greater difference means that I can definitely see how finite this wire actually is. I'm going to have to treat this a lot more like the rod than an infinite wire, as if I had been very, very close. So these are still useful even when we're not dealing with these hypothetical infinitely long wires and tubes and things like that, right? It's still useful. There's just a limit to the usefulness. At a certain point, we have to accept that, you know, the actual length does kind of come into play. We can't just assume that it's infinite. But that's helpful because that means that the flux that we're concerned about is not anything to do with the end caps. It's only the outside shell of our cylinder. That's the surface that we need to worry about. So let's start with a problem here. And this is a problem that we technically already have the answer to. Take that infinite line. of charge with a linear charge density lambda. Find the electric field, or rather, prove, and I can move myself down real quick, but you guys should have this one on your equation sheet. Prove that the electric field from an infinite wire is equal to 2k lambda over r using Gauss's law instead of our integral. Okay, so we knew what the answer looked like, right? That's kind of where we start from in a case like this. I'm going to steal this picture. Let's go ahead and move this over. Let's put it... Oh, running out of space on this one. Took up a lot more space than I planned to, I think. But that's okay. We'll have plenty of space, I think, so we should be fine. Let's go and put this thing right here. Right. So as we have this thing, we've already got our Gaussian shape drawn for us. This makes the whole thing a little bit easier, right? Here is my Gaussian surface. We just need to be a little bit clever with how we define some of these things. So as before, I'm going to start always from Gauss's law. That's just going to make everything a lot easier if we start right there. Electric flux is equal to, when we have a closed surface over the entire surface, E dot dA Q inside over E naught. Okay. So I'm going to focus on the left side again first. Well, let's do these both at the same time. So I have set this up in such a way so that E is always going directly parallel to my A vector, right? As long as I match that symmetry, I chose this particular symmetry, so that would be true. If I had drawn my cylinder halfway up or something instead, where the line is no longer centered, all bets off, it doesn't quite work anymore, right? But as long as I'm matching the symmetry the entire time, E is going radially outwards. It passes right through A, perpendicular at all times to the surface, which means it's parallel with the A vector. We don't have to worry about the dot product. We don't have to worry about the magnitude of E because it's uniform over the entire area A. Nice, right? That's so much easier to deal with. This just becomes EA, where A is the surface area that the field is actually passing through, not the end caps. Just the main body of the cylinder. Now we need to also look at what is Q inside going to be. So let me jump one step down and let's say this is E times pi r squared times length L. Whoops, that's a volume. 2 pi r times L. That's better. What about this Q inside? Well, as I'm trying to deal with this, I know it has a linear charge density, which just means that we could find the charge by multiplying by a distance. What distance? Well, I'm looking from when this line enters the cylinder to when this line exits the cylinder. The cylinder is a length L. Q inside is just L times lambda. That's fine. It doesn't matter that it's one-dimensional, I'm drawing a 3D shape around it. That's fine. That's how much charge I've got, right? That's how we get charge out of a one-dimensional charged object. So now knowing that, we didn't need to do anything else for that step, so let's just carry that down. Now that we're here, the L's cancel out, right? I can divide over everything else that's not E. So this becomes lambda over 2 pi E naught R. Multiply the top and the bottom by 2. And that's fine, right? That's safe to do. 2k lambda over R. There it is. There's our exact same result that we had expected to see from before, right? It's exactly what we proved using that pesky vertical rod integral. But now we've done it with Gauss's law and arguably much easier. At least I think so. I imagine a lot of you do as well. Okay, I'm not seeing anything, so let's go ahead and look at our last actual problem, because this one, we already had the answer. But this one, it's not so clear. So let's say instead of an infinitely long wire, I have an infinitely long cylinder. So a realistic object, right? I'm zooming in a little bit more, and I'm actually looking at this thing, and it has some width to it. The wire has some sort of width to it. That wire has a radius capital R, and I'm still going to say it has a linear charge density lambda, and that's fine to do for a three-dimensional object. That just means if I still multiply it by a length L, I still get a charge, right? That's fine. Find an expression for that cylinder's electric field outside the cylinder and inside the cylinder. You've got to be a little bit clever to figure out how to deal with the inside of the cylinder, but there's a hint here at the bottom. Okay, so let's go ahead and start taking a look at this thing. And you might notice I've made these a bunch of dotted lines, and the reason that I'm trying to do that is I really just want to emphasize more than anything that what we're looking at here, this Gaussian surface is not a physical object. This is a conceptual thing that we are making to accurately describe what the electric field would look like, using flux as a stepping stone to get here, right? But it's not as if we're actually creating this Gaussian surface in reality and using that. This is a thing that we can scale up and down, but it's a tool to find the electric field without needing to go through a crazy integral. So we're starting by talking about the radius of this when it's larger, when R is greater than the radius of the cylinder. Okay, so piece by piece, I'm going to start the exact same way that I've started every single one of these things. Flux, Gauss's law, all this good stuff. Now, luckily for me, this problem is actually, well, identical to what we just did. What's the Q inside? We still have a linear charge lambda. Oh, and this has a length L, let's say. So the amount of charge we have is just lambda times L. That's still fine. The electric field, we still have the symmetry matching up, so this is still E times A is equal to lambda L divided by E naught. The surface area of our cylinder is still 2 pi R times L. The electric field is still 2k lambda divided by R. That didn't change. And here's our second point. When I talked about the electric field from a point charge or the electric field from a sphere being completely identical, and how the point charge may be an approximation, but it still holds true in reality, and it's still a useful tool for us because it accurately describes what happens with real three-dimensional objects, so too does the infinite line of charge accurately describe real three-dimensional wires. It doesn't matter that a real wire has a certain width to it, a certain thickness to it. The infinite line equation still accurately describes its behavior. Now, let's look in the other case where this becomes a little bit weirder. I'm talking, of course, when we are dealing with a cylinder inside of my object. So I'll go ahead and draw this thing out. And again, I'm just going to go ahead. I want to make the dotted lines here because I want to make it clear that this is, I'm not dissecting the wire and placing another cylinder inside of it, right? We're not removing the actual wire. The Gaussian surface is a construct to help us solve problems. So something like that, right? And let's pretend that this back half is actually rounded. Now, we're running into this thing where now R is smaller than the radius of our object, which means it's going to be a little bit more weird. We still have the same setup. Of course, Gauss's law still applies. But just in the same way when we are dealing with being within the spherical shell, now we have to figure out how much charge do we actually have inside. And this is where it's going to get real tricky because we weren't given a charge in the first place. We were given a charge density. Okay, well, I know that the left side, because it's still a cylinder, all of that stuff is going to come right through for us. But the Q inside is going to be the tricky part. So let's think about it like this. What if I took a section of this wire? What if I took a section of this wire and calculated how much charge was on it? Well, if I took a full section of the wire, the charge would be lambda times L. I had that for last time. What if I tried to talk about this in terms of volume instead, though? Well, it would be rho times the volume of my cylinder. The volume of my cylinder is just pi r squared times L. So let's rearrange this in terms of rho. Let's figure out what is rho in terms of lambda. When we divide by these things over, the L's are going to cancel out, and I get lambda divided by pi r squared. That's the relationship between the volume charge density and the linear charge density, right? And that's fine to do. Both of these are totally fine because, again, we keep talking about real objects as if they are one-dimensional, and it still works. So there should be some sort of relationship between tying these two things together, right? A volume and a linear charge density. They should find some way to say the same thing. So knowing that, what we're going to do now is we're going to say, okay, well, Q inside is just how much of the volume I have. This is rho times my Gaussian volume. How much of my Gaussian surface actually has charge inside of it, divided by E naught. We don't have any crazy hollow pieces, which makes V of G much easier to solve. V of G, whoops, I made a mistake. Rewind a little bit. This is not lowercase r. This is not lowercase r. Q, lambda, L, rho, V. This was all talking about my object, the cylinder in black, which means I should be using variables from the cylinder in black. Little r is something for my Gaussian surface. It's not a real object thing. So when I'm talking about rho, I need to be using capital R. Capital R. So when we talk about the volume of the Gaussian surface instead, that is when we can use lowercase r. Okay, so we plug that in. And let's go ahead and plug in rho while we're here. Do you have anything else on that? No, that's fine. Okay, and now the same thing we found for E and A last time. This is E times 2 pi r L is equal to this nasty bit. The pi is going to cancel out over here, but I'm still going to be left with lambda r squared L over capital R squared E naught. Okay, the L's are going to cancel out. One of the R's is going to cancel out. And I should be left with, let's see here. What's still on top? Just lambda? Whoops, and an R. Which we can simplify again to be 2k lambda r over r squared. So, and again, we actually find that kind of same result that we talked about last time, where the charge is increasing as r squared, but the electric field is decreasing as 1 over r. So when we're looking inside the sphere, or not inside the sphere, inside the cylinder, as we're expanding out, the electric field goes as r. And it's a linear increase until we hit the boundary, which, speaking of the boundary, let's test it real quick. What happens when little r is equal to big R? Well, the equation on the left becomes 2k lambda over capital R. The equation on the right becomes a little bit nastier at first. But we see one of the r's cancels out. We are left with, let me make that check mark look a little bit more convincing. we've got the right thing. The boundaries match, they agree. We've got two equations that define the electric field in these two regions around my cylinder. But it's the entire field of electromagnetism is how much work can I avoid doing, right? There's always these general approaches that we've got. There's general approaches that work for any sort of object or anything else like that. But we try and find those cases where we can avoid doing a lot of this work, right? Because when we end up with more complicated things, if we need to define the electric field from a wire bent into a W shape, like, good luck. That's going to be, you've got to do an integral. There's no getting around that. It's just that we have these certain cases where we can avoid doing the complicated bits. If we take a slightly alternative route, we can avoid doing the really, really difficult things and still get to the right answer at the end. It's just that these are special cases. But if you notice, in a lot of these, we really don't end up doing the integrals. Like, I keep writing the integrals, but we don't end up doing the integrals. Not actually, right? We just say, oh, yeah, that's surface area. Stuff like that. All right. Well, with that, we will close out our 24-2 lecture. We have one more lecture. Before exam 2, we are looking at, next time we'll look at conductors and insulators and the differences between those two and how that's going to affect their electric fields, which is something that you've already probably seen in the book, but we haven't really touched upon to this point because it hasn't been as useful. But that'll be next time, and then we'll have a review session, and then we'll have exam 2. But until then,